Question 4 says a rower is capable of propelling a boat at 1.4 meters per second on a still lake. Find the speed of the boat when it is rowed perpendicular to a river flowing at a speed of 1 meter per second. So we want to draw a vector diagram to show this idea. We're going to show the speed of the rower and the speed of the lake, the river perpendicular to the rower. Those are both speeds in meters per second. And we can see immediately that the resultant should be here. We're only asked to find the speed of the boat, so we don't need to worry about the direction at this particular point. So we're just going to use some Pythagoras. Let's give this one a name. Let's call it S. So S squared is equal to 1.4 squared plus 1.0 squared. So S is the square root of 1.4 squared plus 1.0 squared. Which is 1.72. What we want, two significant figures, so 1.7 meters per second. Second part, the angle the boat should be rowed so it crosses said river perpendicular to the banks. So this idea is a bit different. This time we're going to be able to twist the angle at which we row the boat, and we're attempting to achieve a speed, find a resultant velocity vector that goes perpendicular to the lake. So the two vectors that we're going to draw to start off with are the resultant vector. We have to guess the length of it for the time being. This vector is going to be achieved by adding two vectors together, but one of the two vectors is the lake, the river flowing at 1 meter per second, and the other is the person rowing the boat. Now, unsurprisingly, they're going to have to row upstream in order to be able to achieve crossing the lake, crossing the river perpendicular to the flow. So that we've got the perpendicular to the flow. So we're adding the green and the purple vector again, but this time we set them up so the resultant is at 90 degrees to the direction that the river is going in. Once we've set this up, we then just have to decide how we're going to define this direction. I think the usual way to do it would be in this angle here, theta. That would be the direction you describe, I think, the angle from straight across the river. So if we want to describe this, we're going to need to use the tan function. We know the tan of an angle is the opposite side over the adjacent side. So for the angle here, the opposite side here, well, it's empty, isn't it? But we know that this vector of 1 could be placed at this point. We can see it's a parallelogram, isn't it? So we could put the 1 up here. So the size of the opposite side is 1. The size of the adjacent side, no, we don't know. So we don't want the tan function. We know the opposite side and the hypotenuse, don't we? So let's try again. Sine theta is the opposite over the hypotenuse. There we are. So we can see the hypotenuse of the triangle and the opposite side of the triangle. So the angle should be equal to the inverse sine of the opposite side over the hypotenuse. Which gives us an angle of 46 degrees when we write it to two significant figures.